Hi, I'm Yeli. I'm here to present our paper, A Unified Perspective on Adversarial and Out-of-Distribution Detection in the Open World. Deep neural networks achieve near-human performance in many computer vision tasks and have been rapidly deployed to safety or security-critical systems in the real world. For example, autonomous driving and medical imaging diagnosis. However, performance of DNN can degrade severely when testing samples are maliciously manipulated or out of distribution with regards to the training data. Research in adversarial defense and OD detection has been prevalently independent. Furthermore, effectiveness of existing proposed methods has been evaluated in lab settings. For example, benign versus adversarial, or in distribution versus a specific OD distribution. In this work, we propose a light-weighted data augmentation method that reduces DNN's sensitivity to adversarial samples. We investigate the interplay between adversarial defense and the OD detection methods. We attempt to unify them to increase the robustness of classification systems in the open world. Adversarial attacks are hardly perceivable perturbations injected into images that can cause DNN to produce very wrong prediction result. Let X be a testing image, Y is Guangzhou's class label, L is the loss produced by DNN. Fast gradient sign method generate perturbations by taking the gradient of loss over X and then multiply a attacking budget epsilon. PGD method is also gradient based. It iteratively finds the maximum loss within the allowed attacking budget and then project its gradient back onto X. The deep-fold method takes an optimization approach to find an approximation of the classification boundary of testing sample X and the distance vector that is perpendicular to the boundary. The perturbation is added with the goal to pushing the sample along the distance vector to across the decision boundary. Because of a different attacking mechanism, we can see the perturbations injected by deep-fold method is very different than the FGSM method. The goal of adversarial defense is to reduce error produced by DNN when it is under attacking. One direction is to make DNN robust. A straightforward method is to train DNN with a specific threat model, for example, PGD attack. The training process is a min-max optimization paradigm, where one goal is to find perturbation data that maximize loss for the threat model. Meanwhile, minimize the loss with regards to class label Y. The PGD training is extremely slow. One extended FGSM attack into iterative fashion, which dramatically reduce the training time, meanwhile achieve the same robustness as PGD training. The input transformation approach utilizes image processing techniques to remove or mitigate the perturbation injected into images. For example, half-toning operation transform image from intensity space into density space. In general, input transformation are much lightweighted than adversarial training. Some proposed a data augmentation technique mix-up to mitigate the adversarial perturbation. The mix-up method generates virtual samples around the distribution boundary. OD detection. There are multiple OD detection approaches. Some methods use generative modeling technique such as VAE or GAN to learn a latent representation from input distribution as OD feature. Another group of methods utilize softmax classifiers output as feature to design a detection metric. So far, detection methods from the latter group led in performance. Let fx be the output from the last layer of a DNN. A softmax classifier produces a confidence score for each prediction. The baseline method simply uses the confidence score of correctly predicted ID samples to determine a detection threshold. However, when the logic value fjx is very small across all classes, the confidence score can be high, but the sample is likely out of distribution. To overcome this issue, the Odin method introduced a temperature parameter T into the softmax operation. An optimal T value will significantly improve OD detection performance. The optimal T value has to be sought per ID OD test set pairs. As illustrated in this figure, the logic value of predicted class Fix for ID set CIFAR10 and the several OD sets is plotted as cumulative probability curves. For example, for the CIFAR versus uniform test pair, by uniform means a solid block of random color. A detection threshold roughly around 6.5 can detect close to 100% of OD samples, with false positive rate of ID is around 15%. But this threshold will miss out over 60% of OD samples if it is Gaussian noise. Generalized Odin method addresses the temperature parameter tuning drawback by casting the prediction confidence into probability of class label condition over input samples and the input distribution, DIN. With the Bayes theory, the conditional probability is further decomposed into a joint posterior of class label, Y, and input distribution, DIN, and the posterior of input distribution. The H and the G terms are optimized respectively during the training time. Given a test sample X, output of GX is used for OD detection. Effectiveness of existing proposed methods has been evaluated in fine controlled lab settings. For example, benign versus adversarial only, in distribution versus a specific OD distribution. However, in the open world, testing samples can be a mixture of ID, adversarial, known OODs, unknown OOD, and even adversarial OOD. Here is a TSNE visualization of fx, the logic vectors produced by a ResNet classifier over some testing samples that are all predicted as dot class. The ID samples are CIFAR10 dot images, which is represented in green circles. All these samples are numbers from the SVHN dataset represented as blue triangles in the plot. Adversarial samples are generated with the FGSM method. We can see some adversarial samples, the orange dot, are very closer to OOD or adversarial OOD samples instead of the ID samples. In general, there lacks a clear cut between adversarial and OOD. Intersection between the two can be observed. Then, how will existing OOD detection and adversarial defense methods interact with each other in the open world? Specifically, will features extracted from existing adversarial robust DNN classifiers lead to enhanced or degraded OD detection performance? Are existing OD detection methods capable of detecting adversarial samples? Our approach. First, we proposed a light-weighted defensive training method that reduces DNN's sensitivity to adversarial samples. This method utilized singular value decomposition operation to augment training data. Given an image X, SVD factorizes it into singular value, sigma, and orthogonal singular vectors. The singular values are in the descent order. The dominant geometry structure in the image is encoded in the top subspace 1. Here is an example of image reconstruct from the top subspace 1. Most structure information in the image is encoded in the few singular subspace. In this example, with the top 5 singular subspaces, most visual patterns in the original image are restored. Treating the singular subspaces as latent space in generative learning, we designed an image reconstruction algorithm, SV-random. SV-random has 3 key elements: randomness, reduction, and the swapping. Detailed steps is shown in the serial code here. At the training time, images are reconstructed on the fly either by truncating k random singular subspaces, that is the reduction option, or the bottom k random singular subspaces between a random pair of images is swapped for reconstruction. The reduction option reduces noise in images, while the swap option injects noise drawn from the input distribution. In most cases, data augmentation improves classifiers performance. Compared to the mix-up method, we can see our method gives higher performance over both CIFAR data set. Because we are interested in investigating the interplay between adversarial defense and the OD detection methods, we adopt a simple baseline approach for OD detection. However, if a classifier's accuracy is not sufficiently high, for example, in the CIFAR 100 case, detection performance of the baseline method degrades. We propose to utilize multitask learning technique to obtain an extra logic vector for OD detection. Our training objective is shown in Formula A, where Y is class label and the YP is corresponding parent class label. Alpha is a parameter to balance between the loss between the class label and its parent class label. In the CIFAR 100 case, YP is the superclass of 20 types, and we take 0.7 for the alpha value. Now we present the experiment results. First, we discuss the impacts of different training methods. We use the same training schema and the same network ResNet 18 to train all the classifiers. Standard refers to no data augmentation or adversarial enhancement. Mix-up and our method SV-random are data augmentation based. Fast FGSM and half-toning are adversarial training method. On CIFAR 10, we can see mix-up and our method both enhanced the accuracy, while our method achieved the best. While the adversarial training methods both reduce the accuracy over benign ID samples. On CIFAR 100, none of the training methods achieve a better result than standard method. This could be the database is very difficult because there are 100 class and each class has only 500 training samples. However, our method achieved the best among all the 4 different training methods. On the German traffic sign database, we can see that mix-up and our method all improve the performance a little over the standard method, while the fast FSGS method dramatically reduced the accuracy performance, which we can summarize that adversarial training significantly reduced classification accuracy over benign ID samples in trade-off robustness when tested on adversarial samples. We also observed some training methods significantly alter the distribution of FIX, the logic value of predict class, which is the critical feature for existing OOD detection methods. In this set of plot, the detection score produced by the ID set CIFAR10 is represented by the green curve. The 2 blue curves represent scores produced by 2 OOD test sets. Compared to the standard classifier, we can see both adversarially trained classifiers, fast FGSM and halftone, flattened the curves to cause more overlap between ID and OOD sets. This implies a reduced OOD detection capacity. The mix-up method pushed the score of both ID and OOD sets in one direction that caused more overlap between the 2 groups. Whereas our method, SV random plus, pulls the 2 groups of curve apart, resulting in reduced overlap. Now we compare the effectiveness of SV random plus method for adversarial defense. We use 5 types of adversarial attacks. They are white box attack, deep-fall, CW, PGD, and FGSM. Noise is a kind of black box attack that is launched from random points in the image space. The tables summarize classification accuracy under attacks by test sets. On CIFAR10, SV random plus has the highest accuracy under all attacks, result in a 92.3 accuracy on average. On CIFAR 100 and GTSDE dataset, our method has the best performance over 3 out of 5 types of attack. Changes compare the accuracy drop over benign scenario. We can see SV random plus method has the least drop compared to the halftone and the mix-up method across 3 test sets. Since the fast FGSM method was exposed to adversarial samples of the same type or the similar during the training, it is natural the accuracy drop is the least or even increase under CIFAR10 and the GTSDB scenario. However, this robustness is achieved with a bigger performance sacrifice over benign scenario. This figure gives an overview of detection performance of our enhanced baseline method. In the first row, the ID set is CIFAR10, and the OOD set is a combination of 5 test sets. The adversarial OOD is generated by using the attacking method previously used. On the horizontal axis is the false positive rate of ID samples, and on the y-axis the true positive rate of OOD samples. We can see in overall, our method SV random plus outperform the other 3 methods on CIFAR10, also CIFAR 100, and the German traffic sign database. What is surprising that the fast FGSM method performed extremely poor on the German traffic sign dataset. Overall performance. To simulate the open world setting, we evaluate each classifier with a combo test set, which includes one ID test set, 5 types of adversarial attacks generated from ID samples, OOD sets, and adversarial OOD sets. This table summarizes the classification error of each method. With the presence of OOD and adversarial OOD, our method is still a little more robust than the others. Applying OOD detection as a fail-safe controller, our method detects the most OOD samples. As shown in the table, at false positive rate of 10%, our method has the highest true positive detection rate of OOD on both CIFAR and the GTSDB sets. After the predicted OOD samples are rejected, SV random plus has the lowest classification error. Conclusion. In this work, we investigated the interplay among adversarial defense, classification accuracy, and OOD detection. We proposed a SVD-based data augmentation technique and a multi-level semantics-based OOD detection metric to reduce the classified sensitivity to adversarial attacks. Our methods overcomes the performance trade-off between OOD detection and the classification robustness. We conducted evaluations that align with the open world setting. Comparison experiments show that our method is the most robust among the 4 defensive training methods. Thank you for listening.